year and certainly in the second year number theory. So we've seen the definition. We'll see it again right now, of course. I didn't give you guys the reading notes today. Just a few comments on the contents of chapter 3, including the next set of submission problems and towards the bottom.
Cedar.
What's the name of the floor downstairs?
Yeah, I saw Cedar too.
Oh, CETA has. Anyway,
Okay.
let's proceed. Let's proceed. Okay, he starts his chapter 3 with a couple of motivating examples. Okay, now the first one is the system of integers modulo n. Okay, this is what was our bread and butter last year in the number theory and cryptography course. Okay, integers modulo n. When we take the integers modulo n, modulo something, okay, we've got two operations, addition and multiplication. We can find groups with both of these. Okay. For example, here is, well, that's the multiplication type. Let's take Z8. So we can explore these just quickly with the help of Sage. So Sage has in it a command called integer mod ring, which will come up now. I just pressed tab, so it should load the completions of that. Integer mod ring, which can set up the system of integers modulo a certain thing. What we're going to do here is, because that first example in the notes is about integers mod 8, I'm just going to quickly set up the integers modulo 8. For some reason, the tab completions can take a moment to load in. And then once you decide to proceed without them, they suddenly pop up and mess up your typing.
Generates the random. They actually with they use the curve. What they tackled to make us the set of the RG to start with secure network wasn't correct. The actual elliptic curve it was as secure as all the random widget needs to generate in the first place was off.
Right.
So they find.
So wait, is that what you're doing?
Not specific with that.
Not specific with the PlayStation hack.
But it's just like, well,
Oh, come on.
the lads doing crazy stuff. Then nothing matters. Like, I'm actually cares.
Okay, I'll just give this a quick second to redeem itself. If it doesn't, I will continue on.
Yeah, which I was going to go.
It literally was like loading for a good 10 minutes before it just spat out. But it didn't actually.
No, it never got it.
It was yammering it.
On this.
And yeah, it just went like that. And it was literally just across like that.
This
like
should-
this. And he was waiting a good 10 minutes.
This should spit it out immediately as well. Okay, that's not well. We'll return. It'll probably wake up any moment. Okay. Okay, so addition on the integers, modulo 8. That gives us a system which we're quite familiar with, and which is a group. So integers modulo 8 under addition. So they contain elements 1 through 7, or 0 through 7. And we can draw up an operation table for the operation of addition. When you add 0 to anything, it doesn't change it. When you add 1 to everything, it in effect just moves the top row cyclically one click to the left when you add 1. When you add 2, you do the same thing again. You keep doing that. Each time the row moves cyclically one click to the left.
I wonder why you wrote that.
Yeah. So at the very bottom, we'll have 7, 0, 1, 2, 3, 4, 5, 6, 7, 8. Well, that gives you this nice algebraic system. It's certainly a closed system of 8 elements. You add, you operate with any pair of elements, do the binary operation, you get another one of the elements. You have a nice identity element, so when you add it to anything else, it doesn't change it. And associated to any element, there is always a partner element. Sorry, there's zeros underneath the 6. There's a partner element which is called the inverse of that. When you combine those two together, adding in this case, you get the identity element. Those are, and one other important thing, the operation is associative. Associative is something you don't see immediately from the operation table. But, well, addition of integers modulo something we know is associative. That was one of the things we proved about last time. Basically, because addition of the integers themselves is associative. So that displays all the features of the group. Let's see if our CoCalc has woken up. That's quite disappointing.
Maybe.
I'll try reloading the whole thing. Anyway, we'll push on. Now, the question is, and you can do that, there's nothing special about 8. That can be done for any modulus n. You can also do the same thing for multiplication, except not necessarily for the whole system. So can you remember what you need to change if you want to talk about multiplication? If you want all those features to also hold, well, the thing is about the inverses. So if you have Z8, an element A in Z8 has a multiplicative inverse. If and only if, well, the condition is that the greatest common divisor of A and 8 has to be 1. And that generalizes to any n.
I was trying to get that before we did.
The greatest common divisor of an integer with n is 1, then A will have a multiplicative inverse modulo n. Remember, if the GCD of A and n is 1, that means there's a linear combination of them equal to 1, and so this thing will represent A inverse modulo n. So you multiply the two together, you get integer multiple n plus 1. So you get the identity element 1 modulo n. Okay. So that's one example, motivating example to keep in mind. Okay, I'm going to give up on that for the rest of the thing. Jumping around to a completely different context, we will look at a second example. Okay, so that's a numerical thing. We haven't defined what a group is yet. We'll do that in a moment. But just show you a completely different example. Now, this example is the symmetries of the rectangle. So a non-square rectangle. That's a bit longer, a bit wide, whatever. So not square. We think of all the transformations of the plane that will preserve that. These are what we call symmetries. Some rigid motion of the plane. Technical term is an isometry, a distance preserving transformation of the plane. Basically, these come down to either rotations about a point or reflections in an axis, a line of reflection. So these are the things that are allowable as isometries. Well, isometries of R2. It also includes translations, but if you translate the rectangle in distance, it won't be the same rectangle. So there are certain rotations and reflections which might be symmetries of this, and they're listed there. Okay. The first one is the identity transformation, which is the most boring transformation ever, because everything remains the same. But it's included. So doing nothing to the plane is certainly a symmetry. But the more interesting symmetries that tell you actually something about what the rectangle is there's a 180-degree rotation about the center. Okay, we might call that R. Okay. So if you track what's happening to the vertices, A will come up here, B will be rotated around to 180-degree rotation. So B goes around to there, doesn't it? And C goes around to there. CD. Okay, so it's a 180-degree rotation, which is his second one. If you then got two reflections, so there's reflection in the vertical axis. The reflection in the vertical axis sends B, A, C, D. Let's call that V. And reflection in the horizontal axis, which we'll call H. A, D. These are all symmetries of the rectangle. It's the same rectangle, absent the vertex labels. It's the same rectangle on either side that you're looking at. Okay. These are all transformations that preserve the rectangle, symmetries of the rectangle. This system, E, R, V, and H, we can suddenly start to put it into the same, treat it the same way like we treated the integers, modulo addition or multiplication. Okay. So the operation we're using, there's no natural way to add or multiply. But the operation we're talking about here is composition. These are functions. Each of these things is a function of the symmetries of R2. So they're functions from R2 to R2. As such, they can be composed. Yeah. Okay, I've already started using the symbol E for the identity. What you get when you compose the identity with another transformation? It's just the same transformation. So immediately, we can set these down. And we got the definitions on the board there. When you start to look at some of the other combinations, well, what do you get when you compose the rotation with the rotation?
Yeah,
What do you get when you compose the reflection B with itself?
again, I don't
The identity. Yeah, when you reflect in a line twice, you get the identity.
say the horizontal.
Same for H. What do you get? Now remember the convention here in these multiplication tables, it's just like when we address entries in a matrix, it's the row label combined with the operation with the vertex. So this thing here, when we're wondering about this here, we're talking about our operation with the, so this is the transformation of rotating the triangle, the rectangle, after we've reflected it in the vertical axis. We figure it out quickly by just doing these two things, two labels. Right? So reflecting the vertical axis turns it into B, A, C, D, like that, and rotating it 180 degrees, D over here, A over here, C over here, B over here. So this is B, and this is R, so the whole thing is R after B. Well, what do you call that whole transformation?
Horizontal.
H, yeah, because A and D is swap positions, and B and C is swap positions. So this is actually H.
My definition of constant should be B.
So, yeah. Now, if you work it out, in particular, if you track the effect, yeah, you will find R after H is B. B after R, H. B after H.
Rotation.
When you compose two reflections, everything should be back at its original chirality. Chirality refers to like left-handed or right-handed. So when you do reflection, when you look at yourself in the mirror and you hold up this hand, the mirror image raises their right hand. When things get reflected twice, they get returned to their original chirality. And there's only two transformations that preserve chirality, and that's the identity and the rotation. It's not going to be the identity because V and H and R are not. Sorry, this one. V and H are not inverses of each other. So it has to be R. H after R will be V, H after V will be R. So from this very different context, transformations of geometrical figures, suddenly we're playing the same game with it as we played with the integers modulo 8. And all the properties here that we observed about the integer operation table are the same here. And composition of functions is always associated with universal fact, right? The composition of functions. And there's a special function called the identity that plays the role. Every thing as a pair, as an associated element, maybe itself. In fact, for all of these, it is itself. Every element has another element itself, such that when you combine them, you get the identity. It is associative, and you have this closure thing. So we're talking about this set of 4 elements. And every time we do the operation with a pair of elements, we get one of those very same 4 elements. The system is closed. This set of elements with this operation, that's all you need to know. There's no extra other elements involved. It just stays closed within that system. So the word closure. So what we've seen there in those 2 important classes of examples, not the only ones, but they're 2 of the most important early examples. They are examples of what we call groups. Okay. Now, just as the integers modulo something generalizes to all the other integers mod 9, integers mod 10, integers mod 11, so there's an infinite family of cases. There's also an infinite family of cases of these symmetry type groups. And just basically, you take any nice, regular, symmetrical figure in the plane, and you can play this game. You can look at all its symmetries and talk about its group of symmetries under the operation of the composition. And of particular importance is when we take, now the rectangle is not an example of one of those, but when we take the regular polygons. So the polygon's made up from a certain number of sides, all the same length, and just arranged so that all internal angles are the same. So you've got the triangle, you've got the square, you've got the pentagon, you've got the hexagon, septagon, and so on. And you also get this game as well. So there's an example here which you will refer back to again and again, where we take the triangle. Now there are actually 6 different symmetries you can have with the triangle. The identity, rotating by 1/3 of a turn, that is, yeah, each vertex goes 1 click on. Rotating by 2/3 of a turn, each vertex, if you're rotating anti-clockwise, each vertex goes 2 clicks on the second one. And then you've got reflection in the various axes. There was reflection in the axis of symmetry going through the A vertex here, because it's just the C and B that swap. Here you're going through the B axis, and here you're going through the C axis, the axis through that lower right vertex. Now there's a whole chapter on permutation groups coming up in a couple of chapters' time. Jan will be doing it with you. But down the right-hand side here, we've got the permutation representation of each of these symmetries as permutation of the vertex labels. You have 3 vertex labels. The way, remember, this 2-line symbol shows you the function by showing these are the arguments A, B, and C, and these are their values under the particular transformation. Yeah.
P1 and P2 the wrong way around.
They're called row 1 and row 2, so it's the Greek letter rho. But it looks like B. Yeah. So are they the wrong way around? So row.
Should it be for the second one, shouldn't it be CAB?
I think you're right. So here, A. So what was at A?
It's now C.
What was at A? So A goes to. No, here you see A goes to position. See, these are the arguments. So down here is row 1 of A. Okay. So where does row 1 of A live? Well, it lives at position. It lives at the top, which is position B, if you like. Yeah. So Yeah, so that's the way, I think you were just reading it maybe the other way around. So we've got the list of arguments to the function. So argument B, the thing below it is row one applied to B. So when you rotate this thing on one click anti-clockwise, no, sorry, you're right, you're right. I think we probably need to email Mr. Judson about this. So rotate one click anti-clockwise, yeah. Okay.
Anti-clockwise. So C goes
No,
to
no. Okay, so if we understand these as
locations, like point 1, point 2, point 3. A's in point
no,
1.
I think what he has illustrated there is correct. A has gone to position. Is that the position that B had?
Rotated it clockwise.
Yeah, so
clockwise.
yeah, if you think of this as rotation by one click, you have to understand it as clockwise. Sorry, so I misspoke when I said anti-clockwise. But as he's illustrated it here, B has ended up here, which is the position that was occupied by C. So row one of B is equal to C. Yeah.
It works with the reflective ones. If you look at it
Yeah.
as A, B, C, it then looks like A, C, B.
Yeah. Yeah.
That one works.
So no, I think this is okay. Just shows you have to be careful. You know, you have to be careful with what's what. Okay. Okay. So we should look at our. So that's just another example, and we'll be referring back to that various times. This, if you like, this here is what the operation table looks like. So row 1 and row 2 are the two rotations. Mu1, mu2, mu3 are the three reflections of the triangle. And again, just like we drew out there with the symmetries of the rectangle, this has an operation table. This again, we see all these features that we're talking about, the existence of an identity element. Every element has a partner, which is its inverse. Maybe itself. In the case of all the reflections, they are their own inverses. Okay, the system is closed. Whenever you compose two of the symmetries, you just get one of the other symmetries from it itself. Okay. So these are all the aspects that we're seeing in common to all these different situations, and these are all the features that go to form the definition of a group. Okay. So finally, here is the definition of a group. You need a set of elements. So this set could be the set Z8 of all the integers modulo 8, or it could be the set of all the symmetries of a rectangle, set of all the symmetries of a triangle. So some set of elements and some kind of meaningful binary operation on the elements. The binary operation is a function that takes ordered pairs of elements and gives you another element in the set G. Okay. So for example, you compose two symmetries, you get another symmetry. You add two integers mod 8, you get another integer mod 8. Okay. So you need a binary operation on the set. Okay. Here he's representing the operation with a circle. Okay. Other books will represent it with an asterisk in this initial general case when you're looking at the definition of a group. And there are three extra properties that we want the operation to have. We want it to be associative. Okay. You know, composition of functions everywhere is associative. Addition of number-like objects, as much as you know them, is associative. Multiplication of number-like numbers and things very like them, in all the cases you've seen, is always associative. We require that there be a special element called the identity, such that when you operate on any other element with the identity, it leaves the other element unchanged. And for every element, there must also exist in the set an element called A inverse. It could happen that A is equal to A inverse, as we saw in many cases. But in general, it might be a different element. But the property is that when you multiply A by its inverse, you get, in either order, you get the identity element. Okay. So this is what a group is. You've seen a few examples there, the ones we've looked at. And there are a whole host of examples. You can find them everywhere in mathematics, and it's a structure that occurs again and again. And what group theory is the study of of what is common to all groups, studying what the possibilities are for groups. How many different groups are there of a certain size? What kinds of features can you find in groups of certain sizes? And so on. Okay. So following that definition, then he just goes through a whole kind of slew of examples, just to convince you that these things are widespread and can occur in many different contexts. Okay. So the plain old integers under addition is an example of a group. It's certainly a closed set. Whenever you add two integers, you get another integer. Okay. It's an infinite set. Closed. There is a special identity element, which is the integer 0. When you add 0 to any other integer, leaves the other integer unchanged. Every integer has an inverse under addition, more usually called its negative. Yeah. When you
n to the minus 1.
Well, that's that. So n to the minus 1 would how we indicate the inverse of the element normally. And in the abstract, if we were talking about some abstract operation circle, we denote the inverse A inverse. But if you're into the context of addition of integers, the numbers addition of the integers themselves,
yeah,
it would be a bit perverse to call the inverse element n superscript minus 1, because there's a much more appropriate notation already there.
yeah.
It's negative.
It'd be very confusing.
Very confusing. So you should revert to additive notation if it already exists. If it's there and it's already available. Additive.
Okay.
So n, the inverse of n, and you can still use the word inverse, but it's what we would otherwise call
Denotes it as.
the negative. Yeah. The negative. Okay. This operation happens to be commutative. Commutative isn't required in order to be called a group. Okay. Commutative is a property that a group might have. It's not part of the definition of a group. The integers modulo something we've already looked at. They always form a group under addition, but you have to restrict the integers modulo n when you want to look at a group formed by multiplication, because you have to only consider the elements which have multiplicative inverses. Like we wrote on the board a few moments ago, that is all of the integers that are co-prime to n. Now in our number theory unit, we use the notation Zn with a superscript multiplication sign. That's the notation we use for the set of all integers Z mod n, such that the GCD of Z and n was 1. Judson and other authors use the notation UN, which stands for the group of units. Units modulo n. In general algebraic terms, a unit refers to an invertible element. So a unit equals an invertible element, just in general. So you can have some algebraic structures, and some of them are called units, because those are the ones that have multiplicative inverses. Okay. So whenever Judson uses the notation UN, it exactly corresponds to the notation we use in number theory for Zn with a superscript multiplication. Just there's a number of different notations in use. Okay, example 313, the symmetries of the triangle, which we were just looking at, all 6 of them. We looked at the operation table under composition. Another old favorite, sets of matrices. First example is, you see GL2R. So GL stands for the general linear group. Index 2 refers to the dimension of the square matrix. So this is the set of all square matrices of this certain size. So here's 2, but you can generalize it to GLN. And the operation is matrix multiplication. So it's not all matrices, but only those that have inverses. So the condition for having inverses is determined by the determinant in. So if you look at all these 2 by 2 matrices which have non-zero determinant, then they will have a multiplicative inverse matrix. The identity element is clearly what normally called the identity matrix. If you multiply any matrix by this matrix, it leaves it unchanged. Any other 2 by 2 matrix. Okay. You got a nice formula for the inverse. This again is a group. Okay. There's an identity element. Certainly, the system is certainly closed. If you multiply two matrices, two by 2 matrices with non-zero determinant, you get again a matrix with non-zero determinant. Remember, the determinant of matrices has this property, as I listed it there. The determinant of matrices is multiplicative. The determinant of A times B is the determinant of A times the determinant of B. Multiplicative. So if determinant of A and determinant of B are non-zero, so is the determinant of A times B. And so the system's closed and it has inverses. If the determinant is non-zero, there is an inverse matrix. There are loads of different examples though. Okay, GL2R is certainly an infinite example. There's an infinite number of matrices 2 by 2 matrices you can write down with non-zero determinant, if you allow any real entries for there. But there are certain interesting finite subgroups of this. One in particular is called the quaternion group. Now this isn't just plucked out of the air. These things do have geometrical meaning and strong connection, deep kind of meaning in terms of rotations of 3-dimensional space. But just this set of 4 elements, so they all can be represented as 2 by 2 matrices. The identity matrix, which we'll call 1. Okay, this is an example of case where the notation suddenly conflicts with notation used before. So I, when you're speaking of the quaternion group, I is no longer the identity matrix. It's confusing. It's just a non-identity matrix. 1 is what's normally used for the identity. 1, if you like, is a more.
You prefer that one to be called E?
It makes sense,
Well,
but can we
yeah.
pick not have that as I?
I know,
Another
yeah,
letter,
just
there's
for-
loads
Well,
of letters.
Unfortunately,
would have been fine.
I mean, you might at times sit down and decide to re-systematize and notate everything in a consistent way, but the notation developed organically over time, different people, and the first person to write about these, who happened to be an Irishman, Hamilton, who wrote about the quaternions, he picked the letters I, J, and K. So
we did get the memo from before that I was always to be noted as that.
no. He was probably using lowercase ones. Maybe the capital versions aren't so, because they're connected with imaginary numbers, in fact. So this lowercase, this one is connected with the imaginary number I believe.
It looks like K is more.
Yeah.
Oh, it's the imaginary.
Yeah, well, it's all convoluted and mixed up.
Tell it
So
me.
that I is the square root of -1, and so on, and so on. But anyway. No, in fact, sorry. This one corresponds to minus. No, IJK.
Okay.
Anyway, let's not get bogged down. So there are these 4 matrices. Sorry, actually, the quaternions contain the 8 elements. They're positives and negatives. And when you test out the 2 by 2 products, you'll find it's a closed system. Okay, whenever you multiply a pair of these, or their negatives, you get one of the other ones. Okay, so it's a closed system, and matrix multiplication is universally associative. Okay, there is an identity element, the matrix 1, this thing that's called 1, and every one does have its inverse. Okay, you will find. Okay, they are all. Well, 1 is its own. The identity is its own inverse. The inverse of I is minus I. The inverse of J is minus J. And the inverse of K is minus K. So they all have this relation I squared equals J squared equals K squared equals -1. That was the thing that Hamilton scrawled on a bridge, carved into a bridge in Dublin.
Before he jumped off it.
Well, no, when he realised that he'd found the correct way to set up his
I won't
algebraic
forget this.
system.
What have I got to hand?
Well, so the story goes.
At hand.
So the story, and there is a plaque there. The original inscription doesn't survive, but they have a plaque.
They've immortalised it in the same bridge.
Yeah. Okay, and there's another example or two. Yeah, there's just one more example concerning complex numbers. Well, just all the non-zero complex numbers. Okay, so that's our first look at the definition of a group and a whole slew of examples. And when I see you tomorrow, we're going to start doing theory. So we'll start looking at basic properties of groups and the initial theory about subgroups. Okay. That won't take us too long. And we'll then start working on all 54 of the end of chapter exercises. Okay, there's 54 end of chapter exercises. There's some guidance on them.
You can Google the bridge.
No, that's it. Just reminded me on the Eiffel Tower. It
Oh.
has famous names on it. Laplace,
Oh, the plus was one of
Lagrange,
them.
and the genres on it.
Yeah, the ones, yeah.
And I kind of went on there. What is math people?
Broom Bridge, it's called, I believe.
Oh.
Broom Bridge, it's called.
Yeah. It really is the most bridge-looking bridge, but it's the most.
It's the most bridge-looking.
It's going to say.
There it is!
Like a proper old bridge.
It's a quintessential bridge. Yeah.
Oh my god.
So I squared equals j squared equals k squared equals the product of all of them equals -1.
What does that say underneath? Stone of this bridge, what?
Here, as he walked on the 16th of November, Sir William Rowan Hamilton, in a flash of genius, discovered the fundamental formula for quaternion multiplication and cut on a stone of this bridge.
Oh, and
Cut it on a stone of this bridge. So what he was searching for, so people had formulated the complex numbers. They knew about how to algebraically think about the complex numbers and how they related to rotations of two-dimensional space. What he was searching for was the analog of that to treat and capture and represent rotations of three-dimensional space.
it looks like he was. Wait, where is that plaque on the bridge? Specifically, because it looks like it's on the left-hand side there. So it looks like he had a rock and he leant over the edge. And so I'm going to put it here.
I'm not quite sure on the exact location of the
Yeah,
plaque.
maybe. See, there's a walkway there.
Yeah, it's on the canal. It's on one of the. Oh, there it is. Look, on one of the canals.
So it was on the underpass.
Yeah, he was walking by the canal, not along the road.
Yeah.
He was walking by the canal. That's where you'd promenade.
Wait.
Not along the road. You know.
What do you reckon?
You're just walking out. Do you not walk downstream? No.
No,
No, I mean,
actually
either.
not.
But